So today we are going to be starting with AS level chemistry, chemical bonding. The first question that appears is the compound CH3CnAlCl3 has a simple molecular structure. Which statement about this compound is correct? Okay, first to understand which statement is correct, this question is one of the most trickiest in the history of chemical bonding, and you have to understand the structure before answering it. You cannot answer the question unless you don't understand the structure, and the structure itself seems quite complicated. We need to break it down. Okay, let's break it down. First, let's understand that what we have studied in A levels. We know that AlCl3 is a structure that we guys have studied, and this structure N3CH3 is unknown, that we don't know. So let's first draw the thing that we know, AlCl3. So AlCl3 is going to be something like this. Is going to be Al. It's going to have three lone pairs, not lone pairs, three lone electrons, and there are going to be three chlorines bonded to it. Like there's going to be a chlorine here, a chlorine here, and a chlorine here. Now the problem is that you have three chlorines, like 1, 2, and 3. You have three chlorines, but your octet is not full. Aluminum has 1, 2, 3, 4, 5, 6 electrons in its last shell. How many more it needs? It needs 2 more. So now whatever type of bonding is going to occur, there's going to be some kind of happening that aluminum should get a full shell. So what's going to happen is that now this structure CH3 3N, okay, nitrogen trimethylene, something like this. Now let's draw this structure. We're gonna draw it above this thing so that you can understand what's happening in this structure. There is gonna be a nitrogen like this, nitrogen, and it is bonded to 3 CH3 groups. There is, okay, this is going to be complicated. Nitrogen first has 5 lone pairs, 5 lone electrons. Then now we have to draw 3 CH3. Okay, let's color code it because this is going to be a little difficult. 1C, 2C, 3C. It has 1, 2, 3, 4 electrons. 1, 2, 3, 4 electrons. 1, 2, 3, and 4 electrons. And now what's going to happen is that there are going to be hydrogens. Hydrogens are going to be 3 hydrogens attached to each carbon like this. It might seem complicated, but that is what's going on in the structure. And if you don't understand the structure, you won't be able to answer. You won't be able to tell what's happening here. So this is the structure. And now what's going to happen? This lone pair right here, it's going to make a dative bond with aluminum. Why a dative bond? Because aluminum has nothing to contribute to the covalent bond. And unfortunately, aluminum has no lone pair of electron that can bond with this nitrogen. So now this aluminum, it has to form a dative bond with this. There has to be a dative bond. So these 2 electrons are going to be shared with aluminum. So what's going to happen is that this entire structure, it's going to move like this, and there's going to be a dative bonding between nitrogen and aluminum. So that's the structure. And how you're going to represent it? Okay, so firstly you have a nitrogen that's donating electrons to aluminum. You have Cl, 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 and this is going to be a CH3, a CH3, and a CH3. So that's the structure. So now if you understand what's happening here, let's see this. CH3, CnACl, Cl3, whatever, molecules attract each other by hydrogen bonding. There is no hydrogen bonding. Hydrogen bonding is when, okay, I tell you, Hydrogen bonding is when either you have a nitrogen hydrogen bond, if you have a oxygen hydrogen bond, or a fluorine hydrogen bond. These cause hydrogen bonding. Over here, no nitrogen is directly bonded to this hydrogen. The nitrogens are bonded to the carbons. See, nitrogen are all bonded to the carbons. So there's only a carbon hydrogen bond. If I open up these bonds for you guys, if I open up these bonds, let me open them up now. Okay, now I've opened the bonds for you guys, and now see it for yourself. 3H means this. That's the open bond. Yellow. And now you see it for yourself that there's no nitrogen that is directly bonded to a hydrogen. Nitrogen is only bonded to carbon, and you know carbon hydrogen bonds, they are non-polar, they don't cause hydrogen bonding. So there's going to be no hydrogen bonding here because there's no polarity over here. Okay, there's going to be some level of polarity in the nitrogen aluminum and the chlorine aluminum. That's a different thing. But over here, hydrogen bonding is not going to be present. Not at all. Okay, so we rule out the first statement. The aluminum atom has an incomplete valence shell of electrons. Yeah, it's true, but not in this molecule. Only this part of the molecule, AlCl3. Initially it had incomplete, but after bonding to CH3 and CH3 times 3, it's going to have a complete shell. Look at the structure. Aluminum absolutely has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And to get aluminum, it's 2 electrons. That is why it is bonded datively with nitrogen. So this is also incorrect because aluminum has got the full shell. Initially it did not have, but after bonding it has. The bonds around aluminum atom are planar. No, they're not planar. Aluminum is bonded to 4 atoms. So that's going to be not planar. When you're bonded to 4 atoms, that's a tetrahedral shape. So this is tetrahedral, not planar. The last option, the molecule contains a coordinate and covalent bonding. That's correct. Firstly, there's covalent bonding in the molecule. This is a covalent bond, these are all covalent bonds. And this between aluminum and nitrogen, there is a dative bond, which is also called a coordinate bond. So there's a coordinate bond as well. I know this question was tricky and difficult to understand, but trust me, the best way to understand things is to connect what you know. This was the part you knew, you studied, to with that you don't know. This you didn't know. So that's how you figured out the entire structure. You had to make it, you had to see for different things. I know it took time, but that's going to be how the A level goes. The diagram shows the molecule that has sigma bonds and pi bonds. Okay, now again we have to be careful, we have to keep our eyes open. We're dealing with sigma and pi bonds. How many sigma bonds are present in this molecule? So we're only talking about sigma bonds. To find out sigma bonds, I'd always prefer you guys to open up the molecule. To open up, otherwise you're gonna miss. So firstly, this CH2. Let's remove it, and instead of this, let's draw 2H. Because if we see all the bonds, then we can, calculate. Over here, it's a CH, let's remove it and draw an H. It's CH2, let's remove it. Draw H on top, draw an H on bottom. Okay, CH2, H on top, H on bottom, CH. It's going to be a H on top, and CH2, there's going to be H on top and H on bottom. Now let's count the number of sigma bonds. The second bond is the pi bond, so we just have to count the first bond. 1 sigma bond, 2 sigma bonds, 3 sigma bonds, 4 sigma bonds, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. Did I miss anything? 1, 2, 3, 4, 5, 6, 7. I guess I didn't. There are 18 sigma bonds, and the second bond we didn't count because it's a pi bonds. So the correct answer for this is going to be 18 sigma bonds. Nitrogen exists in air as covalently bonded diatomic molecules. Okay, nitrogen has a diatomic molecule which feature are present in N2 molecule. Let's draw it. Nitrogen, this is one nitrogen. It should have how many electrons? It should have 1, 2, and 3, 4, and 5 electrons. And the second nitrogen, this is the, let's make it in a circle. This is the second nitrogen. It's gonna also have 5 electrons. 1, 2, 3, 4, and 5. It's short of 3 electrons, so it's gonna make 3 bonds, triple covalent bond. So what's gonna happen is that this nitrogen basically, so we are having a nitrogen triple bond. Let's see, there are 3 pi bonds. No, the first bond, this one is a sigma bond, the second bond is a pi bond, and the third bond is a pi bond. So we have 2 pi bonds, 3 shared pair of electrons. That is correct. Okay, 2 lone pair of electrons. Yeah, this one's the first lone pair, this one's the second. So option 2 and 3 are correct, which makes C the correct option. Okay, which physical properties are due to hydrogen bonding between water molecules? Okay, hydrogen bonding. What is hydrogen bonding? Hydrogen bonding is basically that you have a OH molecule like this, and there are lone pairs, 2 lone pairs on oxygen. There is a partial negative charge on oxygen and a partial positive charge on the hydrogens. And now what happens is that similar structures, when they are like together, they face each other, what happens is that there is some kind of attraction between this partial positive hydrogen and this lone pair of oxygen. So there is attraction between hydrogen and oxygen. This attraction that is developed is called your hydrogen bonding. So this is the hydrogen bonding, and this is why ice floats on water, because of hydrogen bonding. When this converts into a solid, the volume of ice is more than the volume of water, of liquid. So what happens is, since the volume of ice is greater, what happens is the density is less and it floats. Okay, the HOH bond angle in water is approximately 104. No, this bond angle and the shape is due to the VSEPR theory, valence shell electron pair repulsion theory. So this is because of the VSEPR theory. And ice floats in water, yeah, that's because of hydrogen bonding. What is a higher boiling point than H2S? Yeah, that's also because of hydrogen bonding. This bonding basically increases the melting point of water because there is a force of attraction over here, which increases the intermolecular forces. So it's going to be option number B, which is going to be 1 and 2. Nitrogen and carbon monoxide both have a MR of 28. The boiling point of N2 is this and of CO is this. What could be responsible for this difference in boiling points? CO molecules have a permanent dipole and N2 molecules are not polar. N2 has sigma bonds and pi bonding. CO has only sigma bonding. Sigma and pi bonds have nothing to do with your melting boiling points. Melting boiling points are because of the intermolecular forces. N2 has a stronger N2 bond. No, the covalent bond, like this is your N2 and this is your carbon monoxide. There is gonna be, I guess it's gonna be something like this. Carbon monoxide. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Now oxygen, 1 pair here and 1 pair here. And this is your carbon monoxide. these bonds, the covalent bonds, they don't determine the melting and boiling point. So this is going to have no effect on melting and boiling point. No. The CO molecule has more electrons than an N2 molecule. How many electrons CO has? C has 6 electrons and O has 8, and N2 7 plus 7. 14 electrons, and this has 8, 9, 10, 11, 12, 13, 14 electrons. Both have equal electrons. That's incorrect. The first one is correct, that CO molecules have a permanent dipole and N2 molecules are non-polar. Why is that so? Because in CO molecules, oxygen is more electronegative than carbon. So oxygen pulls these electrons towards itself. So there's going to be a permanent dipole which is represented like this towards the element that is more electronegative, that is oxygen. So there's going to be a partial positive charge on oxygen, and it's going to be a permanent dipole. And for nitrogen, when you have similar atoms that are bonded to each other, N and N, there is no dipole. So that's the story behind it. Crude oil is a mixture of many hydrocarbons ranging in size from 1 to 40 carbon atoms per molecule. The alkanes in crude oil can be separated because they have different boiling points. The table below shows the boiling points of some alkanes. So remember that we are only dealing with one category of molecules, that are alkanes, and over here are their boiling points: 0, 36, 69, 28, 10, 50, and here are their MRs. Okay, so we see that it's not like they're increasing or decreasing, they're randomly arranged, the MRs. Okay, what is the correct explanation for the difference in the boiling point of the three isomers with MR 72? Okay, you have MR72 and you have three isomers of whatever the substance is that has MR72. This is the first isomer, this one is the second isomer, and this one is the third isomer. So we see a variety of boiling points: 36, 28, and 10. So now let's figure out that why is this that they're different. We have pentane, then we have 2-methyl butane, and then we have dimethyl propane. I personally believe that I can better explain this thing to you guys if I draw the structures. So firstly, I'm going to draw each structure so that I'm able to explain that why pentane has a boiling point of 36 but 2-methyl butane has of 28 and dimethyl propane has of 10. So first let's draw the structure of pentane. Okay, let's draw it and understand it that way. Pentane is going to have how many carbon atoms? 5 or 6? Pentane is going to have 5 carbon atoms. So it's going to be 1, 2, 3, 4, 5. And each carbon is going to have full valency. There's going to be saturation in pentane. Why? Because this is an alkane. So it's going to be surrounded with hydrogen atoms like this. Now let's draw the next molecule, that is 2-methyl butane. So for that we first need to, so this is 2-methyl butane. First we need to draw butane, which is going to be 1, 2, 3, and 4. This is going to be butane. It's going to have 4 carbon atoms. Now let's draw 2-methyl. 2-methyl means on carbon number 2, let's start the counting from this carbon. This is the 1 carbon, this is second carbon. So on carbon number 2, we have to attach a methyl group. So it's going to be like this. This is a methyl group, CH3. So this is 2-methyl butane. Okay, let's complete the valencies of carbon. Done with 2-methyl butane. Now let's draw dimethyl. Di means 2-methyl propane. Okay, now we have to draw dimethyl propane. So it's gonna have, first let's draw propane. That's gonna be the main chain. Propane, 1 carbon, 2 carbon, 3 carbon. Now let's draw dimethyl. For dimethyl propane, we need to draw 2 methyl units. 2 methyl units. If we draw, for instance, I say if we draw methyl units on this carbon, CH3 and CH3, it's gonna become, then we're gonna consider this as the long chain, so it's gonna become 2-methyl butane. It's gonna become 2-methyl butane. So we have to draw the methyl chains on this carbon, CH3, like this. Now there's not enough space to draw everything, but I'll try my best to show you guys as clearly as possible. I'll try to show it as properly as I can. Okay, now they're gonna be hydrogens like this, and because it's dimethyl, we have to attach 2 methyl groups. Okay, like this. They're gonna be hydrogens. We have to make it extremely carefully. Hydrogen, hydrogen, hydrogen. Because I need to explain to you guys each and everything here. Hydrogen, 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 and hydrogen. So this is dimethyl propane. So now we see, look at the branching. Over here there is no branching. Over here there is one branch. And in dimethyl propane you can see one branch here, one branch here. And now after seeing all three structures, let's read the statement. Boiling point is dependent upon the length of the carbon chain only. Let's see. Increased branching on the carbon chain increases the boiling point. No, it decreases the boiling point. Look, dimethyl propane has the highest number of branching. It has 2 branches, so it has the lowest boiling point. And pentane has no branching, so it has the highest boiling point. Okay, increased branching reduces the strength of the intermolecular hydrogen bonding. Okay, firstly you should know that none of these structure has any kind of hydrogen bonding. Hydrogen bonding cannot exist between carbon and hydrogen because their electronegativity difference is less than 0.5. So they're non-polar bonds. Carbon hydrogen bonds are non-polar. There is no hydrogen bonding in carbon hydrogen. Increased branching reduces the strength of the intermolecular van der Waals forces. Though there are no hydrogen bonding, but there are van der Waals forces between the molecules. There is always van der Waals forces because van der Waals forces are dependent upon electrons. So it's going to be option number D. I hope you understood the concept over here, that how we increased branching, one branch over here and 2 branches in dimethyl, and how the melting point decreased. Okay, what type of bonding is never found in elements? Ionic. Simple. Why it is ionic? Okay, I'm going to give you example of covalent bonding in elements. Nitrogen and nitrogen, they form a triple covalent bond with each other like this, which forms N2, and N2 is gonna be a molecular structure, so it's gonna have van der Waals forces. Metallic bond is found in all metallic elements. All metallic elements have metallic bonding. Like, for instance, sodium, magnesium, all have metallic bonding. Ionic can only be present between a positive ion and a negative ion. It means between a metal, a non-metal, or a positive and negative ion. Ammonium chloride. There is no metal or non-metal here, but this is a ionic compound. So we know that it is formed between charges, positive and negative charges. So that's why. What is the correct number of bonds in each type in Al2Cl6 molecule? Okay, let's draw the molecule to understand that what's happening in Al2Cl6. Okay, this might be a little trickier or a little difficult, but we love challenges. No, we actually don't love challenges. We're forced, I guess. Okay. So I'm gonna try make them small. This is Al, this is Cl. This is gonna be another Al. This is gonna be a Cl. And this is gonna be a Cl. I guess that's how you draw it. Al, not Al. What am I doing? Okay, let's make Al with a different color so that there's a good color coding. Like this. Okay, so now we have to draw the bonds. This is Cl, 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 and Cl. There's gonna be a single covalent bond like this, this, like this, like this, 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 and these are the lone pairs. You should know how to draw this structure. This is part of your syllabus. So we have drawn AlCl6, but one thing is incomplete. That's a chlorine here. Okay, so now we are done with the structure, and it indeed looks beautiful. Covalent bonds, how many covalent bonds we have? Let's count. 1, 2, 3. When you're proficient, you don't need to draw it, you don't need to count it. Just when you are beginning, try to work hard. Try to make every structure, draw everything, and learn. 4, 5, 6. So we have 6 covalent bonds, and how many coordinate bonds? 1 coordinate and 2 coordinate. So it's gonna be option number B. 6 covalent and 2 coordinate bonds. Moving on. Dicarbon monoxide. Okay, we heard about carbon dioxide, but dicarbon monoxide is a new thing. It's found in dust clouds in space as expected. The structure of this molecule is this. The molecule contains no unpaired electrons. How many lone pair of electrons are present in the molecule C2O? Okay. There are no unpaired electrons. All electrons are involved in some kind of pairing. So how many lone pair of electrons are present? Okay, let's try to figure out. The structure of the molecule is this. This is the structure. Between carbon and carbon, you have a double bond, and between carbon and oxygen you have a double bond. Oxygen has how many pair of electrons? It has initially 3 pair, meaning 6. Out of those 6, 2 are involved here. So there's gonna be 1, 2, 3, 4, 5, 6, 7, 8. So it should have how many lone pairs? 1, 2, 3, 4, 5, 6, 7, 8. Oxygen should have how many lone pairs? 2 lone pairs. Why? Because out of 6 electrons, 2 are involved in bonding. 6 minus 2 equals to 4, and these are 4 electrons. Now we have carbon. This carbon has no lone pair because it had 4 electrons. 1, 2, 3, 4 on involved in bonding. This carbon has how many? 2 involved in bonding, so they're gonna be 1 lone pair right here. There's gonna be a lone pair here. So how many lone pairs we have? We have 3 lone pairs. You just had to figure out the structure. At room temperature and pressure, H2O is a liquid and H2S is a gas, and that's why we are, surviving on Earth, because H2O is luckily a liquid at room temperature, and that's our water that we drink. And H2S, a similar compound, is a gas. And the reason for H2O being liquid is the hydrogen bonding. Remember, why H2O is the liquid is it has hydrogen bonding that H2S cannot have. Why? Because why H2S cannot have hydrogen bonding? Because oxygen is more electronegative than this S. That is why. Okay, what is the reason for the difference? O has higher first and second ionization energies. No, not at all. The covalent bond between O and H is stronger than the covalent bond between S and H. The covalent bond has nothing to do with your intermolecular forces. There is significant hydrogen bonding between H2O molecules but not between H2S molecules. Yeah, that's correct. Okay, C says the instantaneous dipole, meaning the induced dipole forces in H2O molecules are stronger than the instantaneous dipole between H2. Actually the instantaneous dipole of H2S are stronger because it has more electrons. So it is more instantaneous dipole forces, but still H2O has a higher boiling point. Why? Because of hydrogen bonding, making option C is correct. Each of the 4 species in this question are isolated gaseous atoms. Which species is not planar? Let's figure out BF3. Boron is in group 3, so it's gonna have 3 electrons. So this is boron. It's gonna be bonded to 3 fluorines. 1 fluorine, 2 fluorine, and 3 fluorine. Boron has no lone pair around it. Why? Because all pairs are involved in bonding. 1, 2, 3 of boron's electrons are involved in bonding. So there are no lone pairs. So it's gonna be what kind of structure? Boron is gonna form a planar structure, a trigonal planar structure. CH3 plus. A plus means that CH3, first let's draw CH3. So this is a carbon atom and around it are 3 hydrogen atoms like this. And now there was a lone pair of electron here in carbon. There was a lone pair, but what happened is there's a plus sign. It lost this lone pair. So now we have no lone pair around carbon. And now all the bond angles are 120 degrees. All the bond angles are 120 degrees. And this is also a prime example of a trigonal planar structure. So this is also trigonal planar. C2H4 and NH3. It's very easy. Think about it. C2H4. C double bonded to C because it's an alkene. H, H and H. All bond angles are 120. Each carbon bonded to 3 other atoms. There are no lone pairs here. No lone pairs with carbon. These 2 electrons, they're involved in bonding. 2 हो गए carbon के, third and fourth, all involved in bonding. So all bond angles are gonna be 120. For this carbon, it's gonna be 120. This one's gonna be 120 and this one's gonna be 120. Why? Because 3 are arranged symmetrically like this. And for this carbon as well, there are no lone pairs. So all bond angles for this carbon will also be 120 degrees. So this is 120 degrees, this is 120 degrees, and this one right here is also 120 degrees. Coming to NH3, this has a lone pair and you know it. This is gonna be a nitrogen. Nitrogen is bonded to 3 hydrogens. And there's gonna be 3 electrons involved in bonding. Nitrogen has 5 electrons. So 2 are gonna sit on the top and 3 are gonna bond with hydrogen like this. H, H, and H. So the angle over here, initially if lone pair takes a lot of space like this. Initially, if this was not a lone pair, it would have been 109 if it was a bond pair like an H. But since it's a lone pair, it's going to be a little less than 109. It's going to be 107. And which makes the geometry of this molecule to be a tetrahedral geometry. Tetrahedral geometry. So now you understand that why it's going to be option number D. Solid aluminum chloride sublimes at 178 degrees. Which structure best represents the species in the vapor at this temperature? Okay, so we have to show this coordinate bond in which chlorine is giving its electron to aluminum. This arrow shows that aluminum is giving to chlorine. That's incorrect. This shows aluminum is giving to chlorine. No, chlorine has to give to aluminum. Because aluminum, all 3 electrons involved in bonding. And now there are no lone pairs. So this coordinate bond is correct. So this is going to be option number A. Species in the vapor. So in the vapor, we have Al2Cl6. I hope you get all the questions I explained in today's video, and thanks for watching.